Okay, in this video I'd like to talk to you about a particular colligative property, and that is freezing point depression and boiling point elevation. They're both essentially exactly the same sort of thing: freezing point depression, boiling point elevation. Alright. Now, we've talked before about what colligative properties are, those that depend only on the number of particles in a solution, not their identity. And these two phenomena here are something that you guys will actually have seen pretty much every day. If you, let's say you're boiling some water for making some pasta and you put some salt in there, what you'll find is that the water boils. The water takes a longer time to boil than normal. Alright? And the way ice cream is made, the only way ice cream can be made is taking water and cooling it down to below its freezing point, because the colder you can make the ice cream, the better it's going to be. And also, for those of you that have spent any time in Midwestern states where it gets cold and there's lots of snow, people put ice down on the road. The idea is that that salt goes onto the road and it lowers the freezing point of the water there, which makes it much more difficult for it to freeze. Of course, the last thing you want is ice when you're walking to work, and of course you slip and break your, well, whatever. Anyway, so let's talk a little bit about this. There are a couple of formulas that we're going to talk about today that we're going to use in terms of identifying what's going on in these two phenomena. And both those formulas are essentially exactly the same thing. Alright? The first part of our formula is the freezing point depression or the boiling point elevation. F here is F for freezing. If it was B here, we'll be talking about boiling point elevation. The extent of this temperature change actually depends on the concentration of your solution. Alright, and concentration in this terms is molality. Alright, so molality, not molarity. Molality. And the fact is that different solutions will absorb different amounts of solute to a different extent. Every solution, or every liquid I should say, has its own constant in terms of boiling point elevation or freezing point depression. So, for example, water has its own constant for freezing point depression and its own boiling point elevation constant. And there is only one other thing that we have to take into account here, and that is there's a little species here known as I, which is something called the Van 't Hoff factor. And this is an odd sounding thing, but all it is this deals with the number of species that your solute breaks into when it dissolves. And this is kind of an important thing, because this does affect this temperature reduction or elevation. NaCl, for example, if you have 1 mole of NaCl and you dissolve that in water, you don't have 1 mole of NaCl particles floating around, because NaCl is ionic, and so what you get is 1 mole of sodium ions, and you get 1 mole of chloride ions. So in effect that means 2 moles of particles. And the reason why this is important is because this 2 is what goes here. So if your compound is ionic, this I is going to be something bigger than 1. If your compound is covalent, for example an alcohol, like well, for example something called ethylene glycol, I'm sure you're all aware of if you have a car. It's the major component of antifreeze, and what happens is you put it in your car radiator, and the idea is it prevents the water from freezing and cracking your engine block. Now, do you see any metals in this structure? Well, of course the answer is no. It's not ionic, it's not going to split up into ions, therefore I in this case would be 1. So it really depends on what sort of species you have, if it's ionic or if it's covalent. But anyway, this equation here is particularly important, and remember I said it's exactly the same if you're talking about boiling point elevation. Now, I could keep on talking about this for ages and ages, but I think it might be better if we actually look at a particular question and apply this formula. So let's move on to this. This question says, calculate the freezing point of a solution formed when 25 grams of NaCl is dissolved in 500 ml of water. So we have several things we have to understand from here. We're asked to calculate the freezing point of the solution. That assumes we know what the usual freezing point of our solvent is. Of course, our solvent is water. We know the freezing point of water, at least I hope we do. We're also given a volume of water. We're given a number of grams of solute, and we're told what the solute is. The only reason this is important, like I said before, is to know about the I factor and to be able to convert this grams into moles, because we'll need to do that to calculate the molality. Okay? So let's write out our equation first. We have delta T F, because we're talking about freezing point depression, is equal to this times this times this, just like we said on the slide before. So let's see what we can do with this. One thing that I will give you, and the question will always give you if you need to use it, is the particular freezing point depression or boiling point elevation constant for the solvent that you are talking about. And this constant is usually shown in units of degree C per molal or molality. Another way to represent that, I personally find this easier to comprehend because it's in units that I have a better understanding of when I compound them all together. Degree C, kilograms per mole. And this all comes from the fact that when you talk about molality, that is expressed in units of moles of solute over, do you guys remember what goes on the bottom? Well, it's kilograms of solvent. Okay, so we know that we're being asked to find this and ultimately get our new freezing point. We need to get I, we need to get M, and we're given Kf. So the big issue here is calculating M. So why don't we go ahead and do that? You guys have been through going from grams to moles before. Alright, 25 grams. Alright, and we're going to convert from here into moles. If we know what the molecular weight of sodium chloride is, it's actually 58.44 grams, and that actually gives us 0.4278 moles of NaCl. And that's important because we have our moles right here to calculate our molarity, but we need our kilograms as well. Now, 500 ml of water. Does anybody remember what the density of water is? Well, if you don't, the density of water is 1 gram per mil. So therefore 500 mils is 500 grams. And if you remember your conversion from grams to kilograms, of course that 500 mils means you have 0.5 kilograms of water. Okay? Alright, so what we're going to do next is we're going to actually calculate our molality. Alright, so we have 0.4278 moles of our solute, moles of our NaCl, and that's all divided by our 0.5 kilograms of H2O. Alright, which gives us a molar concentration of 0.8556, if I can write that properly, moles per kilogram. Alright, that's our M. So we have our M, we have our Kf. You remember what we said before about calculating I? We just see, is it ionic? And yes, we know it is. We know NaCl splits into Na plus and Cl minus, so therefore that means 2 particles, therefore I is 2. So that means now that I can calculate my freezing point depression. In this case it's 2, that's my value for I, times 0.8556 moles per kilogram. Oops, that should be moles per kilogram, sorry about that. Let me just erase that really quick. And then that's going to be multiplied by the freezing point depression constant, 1.86 degrees C kilogram per mole. And of course, the one thing that we want to make sure we do here is that all our units cancel out. This is a temperature that we're looking for, so the answer we're looking for is going to have units of degrees C, which means everything else should cancel out. You notice the kilograms cancel, the moles cancel, the I is just a number, so it has no units. That means our freezing point depression is this, 3.183. Let me try and write that again. That's supposed to be 3.183. 3.183 degrees C. Now that's not the final answer, so don't just stop there. Okay, that is our freezing point depression. It's not the new freezing point. You remember I said we have to know the freezing point of our water initially? Everybody knows water freezes at 0 degrees C. So therefore depression means the new freezing point has gone 3.183 degrees C below 0. So therefore that new freezing point is negative 3.183 degrees C. Okay?